Yeah, so okay, so I have to reveal something. I was born up in Swansea, but spent the first 7 years of my life here, and then moved further east. And my mum lives in the Mumbles. Okay, right, so I've been here for a while, but I've had an abiding interest in making large-scale systems work. Right, and this is an abiding interest since I was 17, right? So it's a relatively long time ago. And over the years, I went to the University of Bristol age 17. It took me 23 years to get out. Is my standard joke, but they paid me for 20 of them. And then I've been involved in creating startups, getting thrown out of startups because I was causing too much trouble. I'm running my own company now, which is now size 6 or 8, depending on time, on people. And what we've been doing is effectively, for that period, stuff all related to a priori performance engineering. Okay, we describe ourselves as the only a priori performance engineering company in the world, and no one has ever said I'm one of those two. So far, there's no contrary evidence to that. We like to think about how things will scale and perform before you build them. We don't tend to make much money with that because people don't want to know that things may or may not work. We do tend to make our money post-mortem, right? In analysing why things are not working properly, especially when it gets to the point where lawyers are getting involved between companies fighting each other because we are cheaper than lawyers. So we're still cheaper. Actually, it turns out we're cheaper than plumbers as well. But we are definitely cheaper than lawyers. So this is part of what we've been doing. And my motivation, many years ago, I was looking for things. I would ask, how can something run forever? Okay. There's a story by Asimov called "Let There Be Light," I believe, a short story by him called "Let There Be Light." And in this, there's this multi-fact computer, and the multi-fact becomes the system, the global computer for the world, then for the solar system, then for the galaxy, right? And there's this one question that's asked very early on in its life, is how do you reverse entropy? And that process, at the end, you can now work out why the title, right? Because entropy gets reversed. But everybody else looks at it as a nice story, and I look at it and say, how the hell did it manage to keep doing that computation for 10 years, right? How do you do that? So that's that one. I'm interested in systems that are big, and I mean big, this is something you don't tend to experience inside a university environment. When I mean big, I've worked on projects with 6,000 people. Yeah. How do you coordinate, manage, make sure that the bits, when you put them together, actually work? How do you build a system that sits in a lab, works beautifully, take it to the real world and scales, right? As it gets bigger, remains effective and computational. I've worked with several environments in which you have to trust the system with your life. Everything from feature traffic control mechanisms to combat field systems, right? Where you need the life to be beautiful, right, etc. And also things that are robust. And I've been working on this stuff to do with blockchains in adversarial settings. So what you're doing, we're talking about systems working in the real world. People are trying to bring them down. People are trying to attack them. How do you get the system running, right? And as I said, so I've covered, worked with CERN on data acquisition for the air traffic system, worked with National Air Traffic on control systems, combat communication systems, video sign language over 256K modems when that's all you had, right? So that was as well undercut on a blockchain. All of those are not just most of them are not just leading edge, they're bleeding edge in the sense they're difficult things to construct. Next slide, please. So, part of my time, I ran a research institute with Peter here at the University of Bristol, which is one of the usual university things of spinning out nice, good ideas and trying to make money out of them, trying to show that they have all sorts of value to society, And we watched several supercomputer startups spin out of the inbox days, and they failed. And the reason, you say, commercial failure. Actually, a lot of the things we saw fail is because they failed to actually engage with reality properly during the design phase, so that when they got into the real world, they couldn't deal with the effects of the real world on their system. And we'll talk about what those effects are, and hence they were unable to continue to deliver things. So, we work with people, do stuff on prototype versus real deployment. How I know of so many systems that people have put out there that they can't afford to be successful. Were the system to become successful and heavily used, they go bust. Right? This is very true in a lot of this high performance, a lot of the stuff that's going on. It's probably true in AI at the moment, where they can't afford to supply the computation. The computational model doesn't work, but it's very true in telecoms. Okay, and one of the really interesting things is how do you, if you're building a system that lasts forever, how do you get it so the tail end of the, if it's lasting forever, I can tell you the cost of maintenance is going to dwarf the cost of development. Right? And that's an issue that, constructing systems that are sustainable, maintainable, and for something like this Cardano blockchain's aim is to last forever. How do you get the next generation to understand what you did and why you did? Right? So there's a whole bunch of sustainable. Once you put the word forever in there, a whole bunch of interesting issues come up. Next slide. So how do things fail? One of the things that we've basically worked out, we've seen, is that one of the things we've basically observed in the work that we've done is that things can fail. Things can fail for lots of reasons, right? I'm making the assumption that computer science is mature enough, and I realize this is a huge assumption, that it can turn that given no time constraints, you can, and no errors in your system, you can write code that actually works properly. Right? I'm assuming you can construct formal methods, you can build things so that functionally it works. Okay, even with a system that is 100% functional in that sense, you can get these sorts of hazards. One of them is that can it actually work in causality? This DeltaQ will come to this notion. It's the concept of timeliness and quality attenuation, which I will deal with in the next slide or two. And if you have a system, you have a top-level outcome, can you go and put it in the real world and it still deliver that top-level outcome? I have watched, one of the examples, the silly examples was people trying to build systems where they could not shoot friendlies in, right? But to get rid of friendly fire. So by recognizing people and making the trigger not work on the gun if you're pointing at a friendly, okay? Which would, they built them, they got the system to work, it worked perfectly well. They could demonstrate this inside a large warehouse. But the point is that was a 100 megabit per second network inside a small area. You put it into the field, it's not, perfect networking. Take it out of that scenario, suddenly your information has disappeared, it no longer scales. So that's what I mean by failure to meet causality needs. Can it work at the size of capacity? If I built a system and I need 10 million users to make it economic, but actually I can't support more than 5 million on it, or maybe somebody bigger buys you up for some other reason. This concept of a QTA is a quantitative timeliness agreement. Can I meet my timeliness constraints, right, as operational stress? If it's a rainy day and the systems change, can I keep delivering? And what you're seeing here are orders of hazard, right, that people don't even think about when they're designing systems. Right? Can I build it schedule? Does it work? This is a great one. You put two systems together, and this is actually an example of this is in the actually got me some funding many years ago. Many years ago, there was a air traffic control failure in the United Kingdom. It was a failure in the flight. It was a failure of the flight scheduling system, and the flight scheduling system suddenly broke. And it broke because they had taken the way in which it communicated across its paths from a fixed circuit to a packet switch network. They put on a very high-speed packet switch network, but it turned out that the timing changed and exposed a critical path in the code. It would be fine, except the code, the source code had been lost 20 years earlier. They couldn't do anything about this. They had the back end, okay? And then the question that the Civil Aviation Authority asked themselves, well, if we can't do that with a flight checking system, how can we ever consider systems being safe where you're trying to keep aircraft separated? Then basically, they had some money. I got a PhD student investigating some of the problems, okay? But it's those things, so these things do occur, and they're very rarely public. Next slide, please. So, in my time working I worked inside the safety critical centres, City System Centre at Bristol. We had people like National Rail and nuclear electric and various other sort of Lloyd's Register, people who are interested in safety and security and robustness. Somebody asked me a question, well, what is computation? How does it work? And you sit down and you think about it. In a system, in any system, I'm going to say now, please disprove me. If you ask for, you're looking for an answer, you do something, you want a result. That result could be correct, it could be incorrect, but it can be correct but not quickly enough, or it can never turn up at all. The whole thing goes to live log or whatever. But there's a continuum here, right? You want the correct answer, right? And up here there's incorrectness, and you need it in time. And I'm going to say, I think that everything has a time bound. Unless you're willing to wait till the heat death of the universe, everything has a time bound. It might be 1,000 years, it might be 10 minutes, it might be 100 nanoseconds, but everything has a time bound for be useful to you. And the interesting thing then is that the effectiveness of the system, and even its failure modes, failure in this sense becomes failure to deliver the outcome you need in the time bounds which make it useful to you. Does that make sense? This is, I'm now stretching the concept of, I'm saying if it doesn't fulfill the outcome, it's a failure. That's what I'm saying, right? And it might produce the right answer, but if it's 10 seconds too late, you've had it. We did some work tail end of the last century now, funny to say that, in which I got into this in how do you run systems in saturation. And we worked on ways of scheduling and queuing so you can predict the performance of systems as they cross above 100% utilization. How do you build a system so that it doesn't fall apart in a heap, but slowly and gracefully degrades? And graceful degradation is really important in safety critical systems. It's important in any form of infrastructure. If you want to keep it sustainable, if there's a cliff that you don't want to fall over. So the statement I'm making here is that what's interesting is the timeliness of an outcome. And if it doesn't arrive fast enough, it's basically, it's just equivalent to it failing. Right? So notice what I'm doing here is turning a continuous thing, delay, and a discrete thing, failure, non-failure, and turning them into a single concept. Right? And that is the concept of quality attenuation, DeltaQ. So I've stepped away from, what's the failure rate, what's the delay rate? I've turned them into one thing. Next slide, please. So how do you think about this quality attenuation? It's DeltaQ. You can, this is illustrative, and you'll see more and more of the diagram. This is a cumulative density plot, right? What you've got here is you've got something that you require from it, certain percentage of the outcomes in a certain amount of time, which is the blue line, which is the quantitative time, which is part of actually, it's part of a quantitative timeliness agreement. There are other aspects of that when you start thinking about it, but it effectively defines if you're to the left and above that line, good. If you're entirely to the right and below it, bad. If you cross over it, I've got to think about it more. Okay? And the black line is what you might measure or what you might predict right, in a formalism. So the black line represents the real world, either yourself as a model, and the blue line represents the requirement of the system. So one of the things, when you get out, I don't know, you will find people, if everybody wants things to be simple, and they would almost reject forms of complexity, they say complexity is almost wrong, okay? And one of the things that people love is averages. And yeah, there's a famous quote, I think it was Churchill or something, there are lies, damn lies, and statistics, right?
Was this Churchill?
Was it Churchill? It was Churchill. Well, and the thing I would say that there's no quality in averages, right? People will quote averages, and averages, you will see so many things go wrong because people don't think about the edge conditions and things like this. It's a failure to think outside that box that causes problems. We're trying to help people work in a bigger box, right? As opposed to trying to constrain the world to their box, which is too small. And what we have is a relatively, the reason why this diagram is really nice is, imagine you can measure this and you have in a real system, and you can, in lots of real systems, and you have a QTA, and you have a contract. Right, the contracts for the QTA. If you can show the black line is above and to the left of the blue line, you've succeeded. Right? And you will find contractual natures of performance and all this type of stuff. This is where huge amounts of lawyers' fees and people's time get spent. Okay, next slide, please. Is that me putting my own hand up there? So, yeah.
It automatically appears because he lifted his hand.
So, hopefully it's making sense so far, right? So now here's the sort of a bit of mind jujitsu. You know, if you build a system, so make it perform better, they'll ask you to make it perform better. And what I want you to think about is, you know, actually that's probably the wrong thing to ask. It's the wrong goal to set. It's the wrong way of formulating that goal, at least. Let me elucidate. In an ideal world, things would respond instantaneously. You'd press the button and the event would occur. Right? In practice, it doesn't happen, and it can happen has some delay. It may not work, right? Yeah. If you're trying to get here to Cardiff Airport, right? You have a journey. You'd like to instantaneously be translocated from your house to Cardiff Airport. It doesn't work that way. So let's imagine you get in a car. It takes time. There's a possibility the car has a flat tire, so you don't make it in time. You can begin to see that the real world gets into its traffic, right? You know, the car runs out of petrol. There's a whole bunch of failure modes that cause that to get worse. So actually, it turns out that what you want is to view this as removing the things that stop you from succeeding, i.e., it's about managing a privation, right? Privations are things like you can't get a box of silence. I'd like to open a box of silence and make things silent. It doesn't work that way. You get silence by eliminating noise. Okay? You get darkness by eliminating light. You get quality by eliminating and reducing DeltaQ. Right? So how do you achieve performance? You achieve it by reducing the quality attenuation. So instead of adding it, I'm actually taking something away from it. I'm trying to take something, a property away from that system. You can't just do quantity also matters, right? if you're building something and you're trying to make it economically viable, like say the internet, it's reasonably feasible to give somebody a perfect 10 gigabits to their house. Now do that at scale. Now do that for every dorm and house and all the rest of it. That becomes a problem. So you just have to just deliver quality. You've got to be able to think about how to deliver it at scale. Thank you. Thank you. Next slide. Here we go. So what I'm saying is this DeltaQ concept is a measure of the attenuation of an outcome. We'll talk about outcomes a bit more in a moment. It's the deviation from instantaneous and infallible, right? And I'm also saying nothing actually has a zero DeltaQ, almost. The concept of no quality attenuation is an ideal which doesn't exist in practice. So it's always there, right? There's always delay. There's always the possibility of some failure, right? There's a possibility, there is a finite possibility that all of the air molecules in this room will decide to go up into that corner and we all suffocate at this moment in time. But how frequently that would occur is 1 in 10 to the 10 to the 10 to the 10 to the 10, you know, universe lifetimes. So it's not likely to occur, but it's a possibility. It is concerned. Once I've delayed something, I can't undelay it. You may think that's pretty obvious, right? I had a friend in PT who phoned me up one day and he was in shock. He basically said, "You won't believe this, you won't believe this." His name was Achilles. He said, "I've just had someone, a cloud gaming company, turn up and say they want to buy networking services from us, but it'll only work if we can deliver -5 milliseconds of delay." They seriously went to a company and said, "I need the data to revive before I send it." And they thought that was a sensible question. Right? Think of it a second. If you can make data go backwards in time, if you can do this, you can see next week's lottery numbers. You've basically breached causality, right? You've invented faster than light travel. All of those things suddenly happen if you can actually go back in time. But they seriously sat across the table and asked for it as a contractual negotiation item, right? No, that's how badly people understand the world, okay? In the physics. Things can't be delayed, they can't be unfailed. I can make trades, yeah? I can push cars off the road for some cars to go faster. You know, we do this every day. The blue lights that go flashing down the road, people get out of the way. That's how ambulances get through faster. I can take things off the road entirely to reduce congestion. And it turns out that this stuff actually has an algebra, which we'll come to in a minute, which is an interest, because if it has an algebra and you can construct how it composes, you can start to do compositional mathematics with it. You can start to reason about properties of it. You can do meta reasoning about systems. You can solve it in a meta problem, and then it applies to all its physical. You know, there's a morphism into the real world in various places. So the act of having an algebra means that it's not something you have to do every time. You can do a generic problem. It's got a scalability in that respect. Thank you, Peter. Right. So, where does quality attenuation come from? I've touched on it comes from causality, right? You can't, and these things like you can't use a value until it's been computed. You can't get a that's values over there to here until it's been communicated to you. These are the universe restricts you to doing this, and the reason I told you that story about the cloud gaming company is they basically tried to beat the universe, and as Feynman once said, in the battle between what's it sound like aspirations and reality takes a hard negotiating position. Right, you can't get past it. Next one, thank you. Other things happen, synchronization. Right, if you're building software, communication software, sometimes that it's explicit, you're communicating. Sometimes it's data dependencies. You can't do this until these 4 things are finished. It may be to do with I'm sharing something, and I may be, say, sharing a lock. I'm having a critical region. I'm putting it lock on or releasing it. That causes, so that this process affects that process. Or it may be statistical in the sense I'm sharing a CPU. You know, I've got several processes running on the same CPU. I'm scheduling because I have more of them for this, that this one fails, right? And it may be or the bandwidth to the I/O or the bandwidth to the network. I'll tell you. Do you think I should take? I'll tell you a story in a minute about this one. Let's get to the end of the slide. Next one. Process algebras. For those of you who've ever looked at this stuff, start to do a reasonable job of a lot of this stuff. There's extensions to this stuff that's existed called stochastic process algebras, which sort of start to include the statistical sharing of resources. But what we were looking for was not just having all of this in our model, but also having things like resource exhaustion, boundary conditions, exceptions, and failures, putting them all inside the same model. And that's what the DeltaQ framework does. So this is what we've built over the years. By the way, we've been doing this for 25 years, right, building this. How am I doing for time? Not bad. I'm going to tell a story. Go ahead.
I'm very keen. Is this a complete picture for attenuation? Could there be anything else that may cause, but it's not covered in this one?
Okay, so attenuation is an observable thing, right? And what we're saying is there are various ways in which it can be built up. Resource contention is one of them. But what we're saying is I can't think of, there could, no one's thought of one outside the top. I can't say, is there any more? No one's thought of any in 15 to 20 years over above these things, okay? There's not some magical thing. So, things like cosmic rays can cause computations to fail, right? And that's a source of attenuation. It's a very rare source of attenuation. But if you're building air traffic control systems, or I gather people who are interested in moving block or train systems and things like that, those are you have to be able to understand when they occur, how you're going to mitigate them, how you're going to manage with them. And so I said, I don't believe there are any. I'd love to know if there were more. Tell you a story about how this sort of stuff fails. In the early 2000s, I was working with Boeing Space and Defense on future combat systems. And I was in Seattle having lunch, and they were talking about this marvelous new plane they were going to call. It was the 787 Dreamliner, right? And how they'd solved this problem of integrating all the software together because and I can't remember the exact numbers, they had 48 processors, 160 or something software processors on it, right? And basically they had to subcontract this all out. And they basically said it's going to integrate because we have allocated no more than 50% processor for for any of those processors, right? For the software that's going to run on them. Does that make sense? Right? You've got 100% of the processor. There are going to be 3 processors running on this system. You're only going to allow to use 45%. That's less than 50%. That's our risk managed. I choked on my food, laughed, almost fell off my chair, and explained to them that they thought of, on average, that may be true, but they hadn't thought about the timeliness of what will happen, because that's an assumption. Each of those processes will have been designed to, say, use 10% of the CPU. And when they tested it and accepted it, that was 10% of the CPU that was otherwise idle. Okay? And I said, that's not the same as having 10% of the other CPU on which it is otherwise full. In Kennedy, I was in JFK, I had this phone call that said, Neil, it doesn't boot. Sorry, what's up? He said, we put all the software together for the 787, we tried to turn it on, and it doesn't boot. And the reason it doesn't boot is it can't meet all the explicit and implicit timeliness requirements during the boot process. How much do you want? Will you come and live in the States? And I said, look, I'm very sorry. I've had this discussion with my wife. It's either her or you. So therefore, I prefer my wife to you guys. So I'm not coming. Right? Number one. That cost them $1.5 billion. Right? Because basically all of these subcontractors have succeeded. They've passed all their acceptance criteria, and the system integration didn't work to the extent it wouldn't boot. Right? You couldn't switch it on, it would just fall up in a heap. So this stuff's important. Right? Failure to get it right costs money. Next one. Okay. We started off from this sort of this idea of, oh, things aren't perfect. We sort of brought it to the concept that, hey, there's this thing called quality attenuation. It's a privation, and what you're trying to do is shrink it, as opposed to make the quality better, you're trying to shrink the privation. So how do I manipulate it arithmetically, mathematically? What is it? What's a representation of it, right? And what's interesting about this is you can represent what we're talking about as something called a improper, or was it? I think someone else said that's the one, right?
Defective.
Yeah, some people say this word should be defective, random variable. Okay? It depends on which book you read.
No, we agreed to.
Well, we agreed that
actually call it epsilon improper.
Epsilon improper, or epsilon defective. Okay.
The defective was the other one that would not.
Someone had already used it as something else.
Yeah,
okay. So we have this is an old slide. We have a better name for this. But what it means is the CDF doesn't come to one. Right? There's the probability mass. You know, if you you can wait forever and not all things won't actually occur. Right? So does this make sense, right? I'm saying I want a response. It's going to work its way up here. I'm waiting for 10 seconds. And actually what it's saying is that, but I can wait for a million seconds, and I still only would have seen 95% of the possible outcomes. Well, this is how we're binding in the concept of failure into the concept of timeliness. Right? So it combines continuous and discrete probabilities, and it is composable in a mathematical algebraic sense. Why is that so important? Right? This, compositionality is at the heart of abstraction. I can think about this one, I can think about that one. When I put them together, there are things inside that don't affect the outcome, right? If the answer is 42, what was the question? Right? You could decompose it in lots of different ways. That comes from the fact that there's compositionality properties. So making something that has those properties, is really important for a whole bunch of not just academic things, but real systemic things. Okay. Thank you. Right, but you can't talk about, when you start talking about frameworks and things like this, you have to start to become pretty rigid about how you talk about them. You've got to be rigid, precise about what you mean, what things mean. Right. So we have this notion of an outcome. It's very close to what you might think is an outcome in the real world. But what we're saying is it's a well-defined system behavior with observable start and end events. Right? Starts here, ends here. This is the DeltaQ. And the DeltaQ, as a probability mass or probability system, is not necessarily the single observation you made, but all the possible observations you could make of that. If you're a frequentist, it's basically the notion of all of the observations as a population. If you're a Bayesian, right, it's your priors and your likelihoods and your beliefs about the system. It's a probability density function. An outcome diagram is a causally directed graph that defines relationships between outcomes, and it turns out you can take an outcome diagram and the DeltaQs and transform it into the DeltaQ for the whole system. I can bundle in, make it a black box and come on one end. Or I can go the other way. If I want this and I have components, then I can construct constraints on the components. Making sense? Isn't it? The answer is 42, and one of the answers is, the answer is it has to be less than or equal to 42, and I have a 16 over here, then the constraint on this number is this. Yes? It can't be more than, I can't do the arithmetic, but you know what I mean? It can't be more than a certain number. Right, so what we're saying here is this decomposition and hierarchical recomposition is basically what you do when you build systems, right? And you build systems in sort of two ways. You either have things you already have that you're trying to glue together to do something new, or you have an objective that you're trying to meet by building and decomposing. Next, please. So, would you like to go through this is to give an example, here's a system. And what happens is it goes idle, it sends a request, constructs a transaction, it sends it to the request of the network, it receives the request at the other end, it processes that request, it commits the results, it transmits a response, it receives a response, completes the transaction, and we go back to being idle, right? Very simple procedure call type system. So, next. Where are the observable points in the system? Right? I think this is an auto build. You can observe the passage of information, be it a packet or the return from a result of a procedure call or something at various points in the system. And what we're saying is the DeltaQ here is, oh, I'm interested in the timeliness and failure probability of getting from there to there to there, right, all the way around the system. But if I don't care about the back end, I can just abstract it out to it arrives here and it departs here, beginning and end. So I've basically abstracted that away, but I've got its performance characteristics, and I can do this again here, and I can effectively bring it down to this level. And at this level, what you're saying is, this is what I want for my outcome. This is, if you imagine the user's watching, presses the button and gets the result. This is the user outcome you've done. Does that make sense? It's sort of it's not more than sort of adding them up, which is we'll talk about what it means to add in a minute, but that's what we're doing. Okay. Now, I was talking to Magnate for lunch. He said I can either spend 10 seconds or 3 hours on this slide, so you're going to get the 10-second version, right? But I'm willing to talk to anybody who wants to look at this more. You were asking about sources of degradation? Where does it come from? Or what? Well, here are some. You get it. So the thing about is a lot of it's about competition for resources, like queuing, networking, I/O, etc. So you have issues of capacity and schedulability over time, right? You have and that's a time sort of space. The more capacity I get, the less freedom of schedulability I get. So there's, it becomes harder to schedule things in busier systems. There's a space one, right? If I have a communications network, it's easier. It's the density is important, the distance is important. I can do this to myself, or the system can be doing it to me. Individual impact against yourself, system doing it to yourself. I have events that occur from the outside world. They can be random, right? There's no correlation between them. They can be positively correlated, i.e. they arrive in a way that's beneficial to my system. They can be negatively correlated. Rush hours are an example of negative correlation, right? That's why you have queues, we've got it in that sense. And you can have failures and exceptions. So and if you have a failure, if it's frequent enough to affect your outcome, you want to mitigate it. We try and do something else. If it's a really rare event, like my cosmic ray hitting something, then probably I propagate that to a higher level to resolve it. Okay? Because otherwise, if you try to solve the cosmic ray problem, A, you're wasting effort, and B, how do you test it? Okay, so this is what I'm saying is there's a whole bunch of things that lead into here, but they all become DeltaQ. Next one, please. Yeah. So does that, right, before we move on to that, from a system sort of, I'm going to go back and do some examples towards the end. Does that sort of make sense? Does it sort of feel reasonably okay in the stomach here? You can see this. We can go into a large number of deep things later if you want to.
Is that thing, just curious, is monadic? Either you give outcome or some failure. The DeltaQ with that.
You have to. You just use the word monadic as somebody who does functional programming.
Yes.
So what sense do you mean a monoid? Do you mean a monoid or do you mean a monad? Do you mean, actually, this stuff is actually a monoid. It's a monoid, right? So mathematically, it's a monoid, right? Not a monad in that sense. Okay.
What do you mean by this stuff?
Sorry?
What is this stuff that you're talking about? Like, what is the scope of this stuff?
This stuff. Oh, sorry.
What is the this in that this stuff is?
All these outcomes, all the.
Yeah, they are.
All right.
What I've talked about, this DeltaQ concept, the measurement stuff. Oh, sorry, I'm being imprecise with my language here. It's literally inside all of the modeling framework we're doing. It's monadic. Does that make sense?
Yeah. No, like yes, yeah, you're using the subdistribution monads, but yeah, I was just wondering about your precise statement here.
There are a bunch of sub-assumptions going on here, right? Some of those sub-assumptions is that basically a probability distribution is a suitable way of capturing the issue we're interested in, right? And we can go down the end with the thing of how that in a sense is an abstraction of things. So if you're talking about things that are, say, generator functions and not probability distributions, then what we've done here won't necessarily get you a properly accurate answer. But however, I know how to push some of those problems to do generator function. And what I mean by a generator function is where basically the difference between that and a distribution is when you sample it, you sample a random distribution, you get a Bernoulli choice. It has no memoryless choice. Okay. If you're doing a generator function, you can get something who has a bit of history inside it. So because it said 9 last time, it's not going to do 9 now. That type of thing. So there's whole bunches of these fidelity games that you can play too. All the way up to, I give the system the same inputs in the same timing, and I get the same. And it turns out, if you do that, computers are entirely deterministic. If you give them exactly the same environment, exactly the same real time, a whole bunch of things, exactly the same random number of inputs, etc., and you set up everything, turns out you get the same answer each time, right? So, but actually, you can only do that in a real world system. I can't reason about this. I'm making sense here. There's an abstraction, and this stuff, what we've been talking about, is really about the probability and distribution space. But I accept the fact it's not absolutely perfect, but it gets you a long way, a huge way towards not making bad mistakes. Right. So in that algebraic sense, we now have outcomes. Your primitive ones, sequential composition, and now we're getting to the concept, the typical stuff you would see in concurrency, with first and last to finish synchronizations and a probabilistic choice between them. And what we have found over the years is doing simple things of this reveal massive problems in systems. Yeah, if you want to be pure, yeah, and I think that's the best way to say it. And they basically have a semantics. Right, for those of you who are into algebras and semantics, right? We can write out rewrite effect, and these effectively can become sort of rewrite rules for how you can reason about the statements. Next slide. And there's a bunch of equivalences. So we've gone from, talking about performance and timeliness to actually there are transformations you can do with the concept of an outcome. I can do reordering, I can do something. Now, I can do this in a mathematical sense. It becomes interesting, what does that mean in a real world sense, right? I can reason about reordering components. I can reason about doing computations in slightly different ways. And then I can, by just doing that sort of rearrangement on the conceptual board, I can talk about maintaining equivalences. That's what design is. I want this thing to work. Okay, so typically, when I work on this blockchain system, the blockchain has a formal specification. It has a simple step semantics, something like that. Yes, that's what they called it. And basically, it's set operations on state, things like this. All of the work is making that fit inside the time budget. Okay, but having equivalences helps you do things that makes that job a bit more tractable.
Excuse me, can I just add on to this with relation to that question? So the referral to monoids is on the algebraic properties of the particular modeling that we showed the bits of in the past slides.
So DeltaQ is this is a monoid and DeltaQ is a monoid. Okay. Next slide, please. Something real or realish, getting more real. Okay. Here is a description of an outcome diagram. It's relatively, you'll understand in 2 minutes. That's, by the way, it being at one level simple but not lying, it being easy to comprehend is a really important part of enabling people in the design and build space to communicate with each other. Right? You can communicate ideas quickly. I think very importantly, when you come to the graphs at the end, you can maybe be able to communicate with bosses. And bosses are the most complex objects in the design space because they tend not to be able to understand anything. You've got to give them very simple solutions that make sense to them. Pretty pictures are useful, right? So this is a description of something. Here's the outcome. Starts over here and ends over here. It's got a 9995 chance of going this way. It's got a 1.005% chance of going that way, right? I think that's the right number. It's got a, let's say, a 1/3 chance of going this way. Therefore, 2/3 of the time it goes here. And what it does is that's a uniform distribution between 1 and 2, which is then having done something which takes that time, it takes a uniform distribution between 0 and 2 seconds. Right? If it goes this way, then it's got a 66% chance of waiting for half a second and then completing, but that's a fixed Dirac delta pi, or it does a distribution like that. Okay?
I think you understated the boss problem, Neil.
What?
Well, you said they didn't understand. I think it's more they misunderstand.
Oh, okay, right. So I'm being pulled up on, I'm being too nice. It is very unusual for me to be too nice to the bosses. I am being pulled up on that I'm being too nice. Often they will interpret everything in the best possible interpretation for them to be able to lie effectively, to inform the shareholders. Anyway, thank you. So this is making sense, right? And one of my intuition for this stuff is I have some probability mass, which adds up to 100 or to 1, whichever way you want to look at it, and I push it into this system, and 99.95% flows that way, of which 33% flows that way. So I'm sort of pushing probability mass in, and what I'm doing is the probability mass pops out the other end, because it either came out here or here. So this all adds up to 100%, right? And then I am now watching it. It's like I push all these balls in, and I now get a distribution of the delay before they come out. That makes sense? A sort of pink. What's that? Pink. It's got the Japanese game where you Pilico or something like that, right?
You should probably explain what the symbol on the bottom left.
Oh, this is bottom. This is failure, right? There are two. The distinguished values in our algebra or our thinking process. One is the concept of perfection, which is instantaneous and infallible, and the other one is bottom, which is never happened. Right? Always, it takes forever, always fails. Okay? So And what's interesting is you can sort of collect your, if you're doing, well, for example, if you're engaging in reliability analysis, one of the results we've shown is this stuff, you can sort of push all the bottoms and manipulate things so that you can actually get the reliability of the system out without actually having to work out its performance, because it pops out. Because, next slide. So that system has that CDF. We have tools that do this. They're very not so hard. And in terms of visualizing things, you show that to a person and add the centiles. Yeah, go ahead.
Do you have counterexample generator as well that for these days inputs, the system will be here, for example, the bottom one, or some state you said this system will go through this state, and
Go back a slide. Go back a slide.
Yeah.
So actually, I'm not saying the system goes through that state. I'm saying conceptually,
what possibility that it may be?
No. I'm saying in the what I said probability mass, like I push it in and it pops out the other end. Another way of looking at it is that you run this experiment in multiple universes at the same time, and you aggregate the results of all the universes. Okay.
Well, I'll talk after this.
Yeah, afterwards. But what I'm saying is this is sort of it's sort of taking a Bayesian view of what will happen. Okay. Right, Mom. So the visualization here is to help people move away from averages, and people think of averages, people think of rates. Little diagrams like this where they themselves can engage in. Well, I wanted this to work in 3 seconds, and he said, well, look, this is what it's going to do. It will work in 3 seconds 80% of the time. Is that acceptable to you? Right? They can make a judgment call. Well, you're informing people to make judgments. Next slide. When you start working with rare events, you're interested in the tail of the probability and how does it collapse at the end. So you can look at it this way, right? This is the inverse log of the probability mass. So in lots of systems, those rare events actually have a huge impact because they force you to retry. For example, in communication networks, the loss of a packet typically will require another packet to be sent. In worst case outcome, it requires a timeout to occur before the other packet is sent, right? Okay. So basically, these things become interesting, and sometimes you want to think about frequencies. And this is the sort of uniform convolution of two uniforms. This is a uniform over here, and this is actually there is no representation of the PDF of the Dirac delta function because it's an infinite amount of probability. It's mass in a short period of time. We sort of make a nice vertical line to express. So you can see that there's something happening like this, but it happens there. Then there's a bit over here, and then the rest occurs there, and the sum of that is 99.95% of the time. Yeah. Sort of making sense. You can feel the diagrams are giving you some knowledge. Now okay. So I'm almost going to the end. What's the time doing here? Actually, pretty good. How does this help? Okay, I've talked about measuring systems, doing things. Maybe this does. How does this help you design and think? So let me just give you a very simple example here. I have a system that has a uniform. I have a component in my system. The outcome of that component is it takes a uniform distribution between 0 and 1 second. Nice, simple. That's the component. You can sort of relate to that, right? Now imagine I'm going to put that, and that, the CTF of that is the blue line. So it starts there, uniform up to there. Imagine I put 2 of them and to take the first to finish. Right? What do I gain? Right? So I've spent enough resources to make 2 of them, and now what I've gained is that green line. Okay. I now can get to the 80th percentile quicker than here. I can spend 3, 4, 5, 6, and every time I'm spending, I'm adding linearly increasing the cost. I'm getting less and less of what I put in. This is the law of diminishing returns here, is you can actually quantify what's happening. Right? Does that make sense? And if you're designing something and you're engineering something, and an engineer is something that does for a dime that any old fool can do for $1, working on costs and, you know, there is always this trade-off of resources and costs and energy, and you have to come up with a solution. You have to come up with informed design choices. This helps inform the design choices. Okay, now that's first to finish. This is what happens in the last to finish world. Right? Notice, you know, you have to wait for 1 to finish, 2 to finish, right? And you can look at that and say, yeah, that sort of fits roughly with my intuition. Okay. Now let me ask you a question. From that, if I were to say to you, imagine I have a system like this, and it's uniform, but it only succeeds 90% of the time. What's the first and last to finish synchronization going to look like now? Can you visualize that? Right. Next slide, please. That's what it looks like. Right? You could basically say, oh, well, I know that if our first to finish synchronization gets there, and I can understand that, that seems reasonable. And then, oh, look, they get better and the risk gets better. And it turns out that, you know, the failure rate for this one is what you would expect when you think about it from a reliability point of view. It's 1 in 10 to the -8. Over here, that was 1 in 10 to the 1. Over here, when you put them sequentially together, you end up with graphs that you expect, which look very much like the similar one, but the failure rates, they don't all fail together because, of course, in order for it to fail at the 8th one, it must have not failed at all of the previous 7. So you could do the arithmetic and do sort of simple probabilities once you think about it. We're doing this entirely in the tool and it's coming out with the right answer. And of course, if you've got a combine first and last to finish together, you've got voting systems in safety critical, right? You know, you will basically take the majority of result from 3 processes, right? Which is a last to finish synchronization of a first to finish of a set of first to finish synchronizations, right? Etc. So you can start building up more and more complex abstract components and think about them abstractly and inform your design decision space. Okay, and what this means is you just don't try to build things that are impossible. So at that point, I think I've finished the technical input. So what are we doing here? You know, why we come to sunny Swansea, etc. And that's unusual. I realise sunny Swansea is an unusual event, but you know, so what we've been working together. We've done work with a whole bunch of people, and we're looking at how we're going to do next. You know, how are we going to build this material? What are we going to do next in the algebraic interpretation? How are we going to improve the visualization? We have a whole bunch of work that we do with people about measuring networks. It's even an international standard. The mathematics of this is an international standard for measuring networks. Okay, using network measurement. You know, what are we going to do there next? And you know, we're going to talk through lessons learned in blockchain reliability and things like that. Thank you for your time and listening to me. This is a set, you know, apparently this is what we have to do these days, a set of logos of people who've contributed towards what you're doing. And, you know, people like Lucille Levin, IOG, Vodafone we work with, but even Innovate UK and people like that have funded little bits of this work along the line as we have done other projects with. Thank you. Questions? Sort of, you know.